So this week, today we're going to do 11.3 and 11.4. That wraps up chapter 11. On Wednesday, which is an X day, we're going to do the chapter 11 quiz. We'll worry about some kind of review assignment when we get back after spring break, but then we'll be taking the chapter 11 test shortly after that. Everybody cool with the plan? Okay. So in chapter 11, in 11.2 and 11, or 11.1 and 11.2, we talked about indefinite and definite integrals. So let's just start with a little review problem here. If I want to do the integral from 0 to 3 of 30 dx, notice this is a definite integral. How do I know it's a definite integral? By looking at it. Has the bounds of integration on there. That means it's a definite integral, which means that my answer here should be a number, not a function. But I start the same way I would for an indefinite integral. I'd start by finding the antiderivative of 30. What is the antiderivative of 30? So I add 1 to the exponent of the variable and then divide by the new exponent. And then we'll evaluate that from 0 to 3. So I have the upper bound plugged into my antiderivative minus the lower bound plugged into my antiderivative, which just gives me 90. But there's a geometric interpretation for what we've just done there. So if I think about this, here's like an XY axis. Here's like the line y equals 30. Here's like x equals 0, and here's like x equals 3. If I look at the area formed by under the curve that's bounded by the bounds of integration, well, this is a rectangle that's got a height of 3 and a width, or a height of 30 and a width of 3. What do you notice about the area under the curve and the value of the definite integral? They're the same. Guess what? They're always going to be the same. Wonderful. So that's another interpretation of what we mean by doing an integral. So let's look at a slightly more complicated example. So let's look at C here. So it says we have the function negative x plus 5, and we're looking at it from negative 1 to positive 1. So if I plug negative 1 in for x, I get negative of negative 1 plus 5, so that's 6. 1, 2, 3, 4, 5, 6. And if I plug positive 1 into x, I have negative 1 plus 5, that's 4. What type of shape do you guys see here? What type of shape is this red thing? Trapezoid, very good. What's the area formula for a trapezoid? It is the average of the bases times the height. So the bases are the two verticals, that's 6 and 4, and the height is the distance along the x-axis, that's going to be 2. So I get 10. Mr. Kulik, what if I don't remember the area formula for a trapezoid? Could I have done like chunk this into like the area of a triangle plus the area of a rectangle? Why, sure, you could do that. That's fine. You'll get the same result. Whatever's easier for you. I like trapezoids. I'm not afraid of the trapezoid area formula. I had that memorized back in, well, I was a little whippersnapper, so. But if you don't remember it, it would be on your formula sheet for the IB exam. It's not really a sheet, it's a packet. But, feel okay there? Let's look at D here. Now, everybody hopefully had no problem noticing that what the graph of h of x was going to look like, right? It's just a straight line. What is the shape of the graph for c of x going to look like there? Nobody knows? Any guesses? All right, let's ask you this question then. What's that the equation of? Nah, man. I mean, yeah, but what shape graph does this make? No, man. You guys are, it's a circle, man.
No way.
Now, in general, for a circle with center h comma k, we'd say this. And if I rearrange this to try to get the y by itself, I'd have something like that, right? And we square root both sides. And then we can add the k over. Okay, so this is all still representative of circle. Now, if I look at this here, this last form, and I look up here at C, do you see that they are the same thing, or almost the same thing? What's the difference? What's my value? Well, first of all, what's the big difference between the two formulas? That'll affect the shape. Do you see a plus or minus on this one? On C? Or I'm sorry, D, C of x. Is there a plus or minus on that? Nope. What's that mean? Am I going to get the whole circle? No, what am I going to get? Half a circle. So this guy's going to be a semicircle. You good with why it's a semicircle? Because there's no plus or minus. All right. So the next thing I'm going to look at, is there anything being added or subtracted outside of the square root? There's not, right? How about anything paired with that x inside of it squared? I don't see anything there either, right? So that tells me that circle is centered at 0, 0. This piece tells me the radius. What's the radius going to be? Two, right? If that's r squared there. So to graph my circle, my center's here at 0, 0. I have a radius of 2, and it's only a semicircle. It's only the positive half of it. So there's my graph. So that's the area under the curve. How do I compute the area of that figure? What's the area formula for a circle, guys? That's the circumference, 2 pi r. Pi r squared. But there's a semicircle. Yeah. And the r here we said was 2. So our area under the curve is 2 pi. Is everybody okay with how we did this? Now, we could check each one of these if we wanted to using our calculator. I mean, honestly, we could do the first example by hand, but we wouldn't want to do this. You guys don't have the calculus tools to do the second one by hand. But we can do both of these on the calculator. If you don't remember how to do that and you'd like to follow along, I invite you to take out your graphing calculator if you wish. If you don't have yours and you're like, man, I want to follow along, and grab one of these bad boys off my desk and follow along with me. So, from the home screen, what I'm going to do is I'm press the math button. I'm going to pick command 9, fnint. That stands for function integration. So if I was going to do the first one, notice I get 10 just like I did geometrically. If I were to do the second one, I get this decimal. Well, that's a kooky looking decimal, Mr. Kulik. I thought you said it was 2 pi. Yo. It's 2 pi. Why isn't it exactly? Why didn't the calculator give me exactly 2 pi? I mean, it's pretty close, but it's not exact. Why isn't it giving me the exact value? Because the calculator can't actually do calculus by itself. What it's doing is a really accurate approximation. So like when you get out to that 4th, 5th, 6th decimal place, like you may not get the actual exact value anymore. It'll be pretty good though. Because on an IB exam, what's your rounding spot at? 3 sig figs. Look pretty clean at 3 sig figs? Yup. That approximation will do. All right. What if we ask you to find the area enclosed by the curves f of x and g of x as written here? Yup. And the x-axis. Well, we should look at the graph then, right? So let's take a look at this. So let's type these in. So we have cube root x plus 3, and then what was the other one? Negative 2x minus 2 cubed. Okay. I'm going to just, I don't know what my last window, I do this stuff all the time. So I'm just going to go to Zoom Standard here. Okay. So if I look at my picture, the area enclosed by my two curves and the x-axis is like this region here, right? You guys see what I'm talking about? Everybody agree? So to do this, what I'm going to do is I'm going to break this into two integrals. So I want the area under the blue curve until they intersect. And then I want the area under the red curve until it hits the x-axis. Everybody good? Okay. Where's the blue curve hitting the x-axis? Looks like x equals negative 3, right? You guys agree? Where does it look like the red curve is hitting the x-axis? Positive 2. Where are the two intersecting? Maybe, but what if it's not exactly 1? Right, the other ones, it's like, well, if I plug negative 3 into this, I get 0. If I plug positive 2 into this, I get 0. I'm pretty confident there. The other piece, though, it looks like it's 1, but what if it's not? Is there a way I could find that value exactly? Second, trace, intersect command. Since I have only two curves in one intersection, I can just press enter 3 times. It is happening at 1, but probably wanted to check and be sure. So my plan then is going to be the integral from negative 3 to 1 of f of x dx plus the integral from 1 to 2 of g of x dx. Everybody good with the plan? To do that, I'm going to use my calculator. So I'm going to go back out to the home screen. I'm going to do math, command 9, negative 3 to 1. Now, I could type in the square root of x plus 3, but I already typed that into the y1 spot. So instead of typing in square root of x plus 3, which I could do, I can also type y1 here. That's what I'm going to do. So I'll press vars, yvars, function y1, and then plus math, command 9, 1 to 2, and then I need my y2 here. Again, I could type in the function over again, but like, I already did it once. And that ought to do her. So we'll call that 5.83, rounded to 3 sig figs. What do you guys think on that? It's all right? Worth noting that you could not have done this integration by hand with the tools you have available to you. My AP Calculus students could do these. You could not. Last example for 11.3 says a ramp for skateboarding has a side piece that's modeled by the area enclosed by the y-axis, the x-axis, the function f of x is equal to 1, and the curve g of x equal to yada, 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 with all measurements in meters. Use your graphing calculator to sketch the shape of the side piece. Okay, so let's grab that. So we have y equals 1. Then we have that other complicated mess there, 3 minus square root 9 minus x minus 3 squared. Everybody's okay there? Since it's bounded by the x and y axes, I'm just going to go from 0 to 10 on both x and y because I'm really only concerned about the first quadrant. So it says a ramp for the scale has side piece modeled by the area enclosed by the y-axis, the x-axis, y equals 1, and this curve. So if I look, here's the x-axis, the y-axis, the curve, and then y equals 1. So it's like this little corner piece. Everybody cool with what we're talking about there? Okay, and it's asking me to then compute that area. So what I'm going to need is the area under the blue curve up to here, and then plus the area under the red curve from that intersection down to where it hits the x-axis. So going to need that point of intersection. So let's find that. Now here I have to be a little bit careful with my guess because I have 2 points of intersection. I don't want that one over there. I need to make sure my guess is close to the one I want. So 0.764. And then from that point of intersection up to where it touches the x-axis, which looks like at 3, which would make sense because 3 minus 3 is 0, and then the square root of 9 is 3, so 3 minus 3 should be 0, so that tracks. So I won't bother finding that on the graph. I guess I could call this f of x here. And now it's just calculator time. And then that's y2 now. I went and retyped it in there. Again, I could retype it again, but you know, I'm not super interested in that. So I get 1.45 rounded to 3 sig figs. Is that okay with you guys? Okay. What if instead of giving you guys a function defined with an equation, what if I give you a function that's just, you have some points, like some data. So instead of giving you a smooth curve, I've given you data and I ask you to approximate the area under the curve. So there's kind of a couple different ways you could approach this. Okay. One way would be to build rectangles here. And there's 2 ways that are plausible to build those rectangles. So one way would be using the left-hand endpoints to build our rectangles. The other would be using the right-hand endpoints to build our rectangles. Another might be to do trapezoids. What do you guys think? And then just add up the areas of each of these ways of doing it. So again, if I did left hand, I would have, this is 12 high and 2 wide. This one was 17 high and 2 wide. This one was 18 high and 2 wide. And this last one was 16 high and 2 wide. If I did it using the right-hand rules, I'd have 17 high and 2 wide plus 18 high and 2 wide plus 16 high and 2 wide plus 15 high and 2 wide. Or if I did it using trapezoids, I'd have 12 plus 17 over 2 times 2 wide plus 17 plus 18 over 2 times 2 wide plus 18 plus 16 over 2 times 2 wide, and then 16 plus 15 over 2 times 2 wide. Right, so depending on what the instructions ask for, you could do this problem several different ways, using left-hand rectangles or right-hand rectangles or trapezoids. So you just have to pay attention to the directions. What this process is, though, of like approximating the area by building these rectangles or trapezoids, this is called a Riemann sum. Named after German mathematician Bernhard Riemann. And this is actually the rigorous definition of what an integral is. It's basically adding up rectangles to approximate the area under the curve, except using infinitely many rectangles. So it says here, use the trapezoid rule to find the value of the integral from 0 to 8 of 2 to the x minus 8, or the absolute value 2 to the x minus 8 dx using trapezium that are 0.8 units wide. So I'm going to just refer to, for my notation, I'm just going to refer to this as f of x, that absolute value function. So since they're all 0.8 units wide, I can factor out that height and just apply it to everything to make the computation a little less cumbersome to write down. So I'm going to have f of 0 plus f of 0.8 over 2 plus f of 0.8 plus f of 1.6 all over 2 plus f of 1.6 plus f of 2.4 all over 2. Gonna have 10 of these bad boys. And I'm just gonna go down to here. So if you count up, I have 10 of these base 1s plus base 2s, right? Notice we can simplify this down a little bit. Since everything is over 2, I can factor that out, right? And basically ditch this part. Everybody okay there? And then notice that other than the very first and the very last, I have 2 of every other base or every other height. Do you guys see that? Is everybody okay there? Will it be this way every time I do a trapezoid rule? Where I have 2 of every single base except for the first and last? Yes. So to do this now on my calculator, what I'm going to do is into y1, I'm going to type in my function here. So math, number, ABS to get the absolute value. Then I have 2 to the x minus 8. So I have 0.8 divided by 2 times, and then I'll do y1 of 0 plus 2 times y1 of 0.8 plus 2 times y1 of 1.6 plus 2 times and just kind of keep grinding this away. Oops. Made a little mistake there. We'll clean it up here at the end. That should be a 2. What is my syntax at? There. Okay. So there's my value, or my approximation. Notice I could find the exact value by just doing the integral from 0 to 8 of that function. Right? Pretty close. Decent estimate. What would I do to be able to improve this estimate? Is I just make my what do I call them? My widths of the trapezoids, make those smaller. The smaller the width, the better the estimate will be. And when they become infinitely small, infinitely narrow, as they approach 0, it'll be the same as the definite integral. Okay. So the velocity time graph shows a train journey. Use the trapezoidal rule to calculate the total distance traveled by the train. Okay. So basically, I'm just going to slice these into, like that. So the first slice is just a triangle. So I have 1/2 base times height. The next 2 pieces are rectangles. The next piece is a trapezoid. Yup. Then I have another trapezoid. Then I have 3 rectangles. Then I have another trapezoid. That's 180, 60, 40. And then I have one last little triangle there at the end. And that ought to do her. I just type that in my calculator and press enter, and bingo, bango, bongo, we are donezos. And that's all she wrote for for sections 3 and 4. That'll wrap up chapter 11 for us. For your next class, for your quiz on chapter 11, that's going to cover sections 11.1 and 11.2. So you should be able to find general antiderivatives. What's the rule that you do to do that? It's this, right? Find the specific antiderivative given a boundary condition. That means you're going to plug in the x and y when you're done with your antiderivative and solve for c. find the definite integral by hand and with a calculator. You should know how to do both. And then be able to do an integration story problem. So given a rate function, calculate the accumulation. Right, we talked about that last time, how we can think about integration as an accumulation of a rate. Right, if you collect, if you go for a certain velocity for some amount of time, what you've accumulated is a distance, like a change in position. But that's it for me for today. Any questions about what we've done today? You guys were very sleepy seeming. You guys getting enough sleep at night?